Hello and welcome back to this series of emulating RISC-V in a high-level language. So I left up abruptly last time, scratching my head at a bug, and after some offline debugging, I found the cause. So let's just jump into it and finish up our work. So here is the bug that I found. We were looking at the store instruction and we were using the inappropriate place to fetch the information that decodes to the source register that we're using to store the data with. And it was wrong for both store byte, store half word, and word. So I fixed it for all three cases. All the unit tests pass. And now finally we can go back to our code and run it. And recall that last time we came to the conclusion that the result should be 35, and indeed it is. So, feeling very happy about that, we're going to challenge ourselves even further, and we're going to write one of the standard tests, which is the recursive implementation of the factorial function. So, if you don't remember what a factorial function is, it's the product of all the numbers starting at a number n and then decreasing all the way down to 1. So 1 factorial is 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 3 times 2 times 1, which is 6, and so on. And this function grows very, very quickly, which means that once you start moving into the teens or 20s, you run out of space and you can no longer store the result in a 32-bit number. So it's not a very practical number to compute in an integer register that is only 32 bits large, but the point size is to verify that we are successfully computing a recursive function. So a good approach is to start by writing this in C# in a high-level language, and then, as usual, convert it back down to assembly language manually, and then we'll verify that the result is matching the original result in the factorial. So let's start by creating a function called fact, and it's going to return an integer, and it takes a number n as its input argument, and the factorial definition first checks to see whether n is less than 2, and if it is, then we know that this is the base case of the factorial function, and the value should be 1. However, if the factorial number is larger, then the result is actually n times the factorial of n minus 1. So here again we see a situation where the input parameter of the function is being used after a call to a function, which means that we have to be careful about managing the value of n. And also it's a recursive function, which means that we have to be careful about managing our return address, which is the value that comes in the x1 register. So this is our C# original, and let's evaluate factorial of 10, which is should be in the millions. And we'll get rid of this for the time being. And let's run this to make sure that our code has a good base case. Oh, what's going on? Didn't I not write the factorial function correctly? Let's see. if n is less than 2, well, let's put a breakpoint here and see if we're... Oh, hold on a second. We're running the emulator, aren't we? No, we're not. Okay, so let's try debugging this and see why we are spitting out. So here we go. N is 10, and we execute, and now n is 9. And so this should only happen 10 times. And there's our 1. Now we have to return 10 times. There's our result. Okay, so I'm not sure what happened there, but here is our result, which is 3.6 million. Great. So what we want to do now, I'll just quickly put that in here. And this is the C# result. And then what we'll do is we'll have the assembler result. Great. So let's write our assembler version of the factorial function, the recursive factorial function. So recall then that if you have a function that takes a parameter, the first parameter will be in register x10 using the calling convention that we discussed last time. So n coming in is going to be x10. Now we need to compare it against 2. So a way to do that is we need to create the numeric number 2 somehow. So we will say, let's put that into register. Well, we are only going to use it here, so we're just going to discard it. So we can put it in a temporary variable. Since we are not using x11 coming into this function, we can use it as a scratch register. And that is allowed because the input parameters of a function do not need to be preserved by the function. So we can use it as a scratch variable. So what we'll do is we'll say, here, well, let's do this a little bit high level. The first thing we need to do is save n, because we're going to need it at the end of this function. So we'll say save n on the stack. So how do we do this? Well, first of all, we need to make some space on the stack, and the way to do that is to subtract a number from the stack pointer, which was in register 2. So we'll say add immediate to the stack pointer, which is register 2, the existing current value of register 2, and then minus 4. We'll start with that. We may need to adjust this later. So now we have decremented the stack pointer by 4 bytes, which means that now there's a slot available to store the incoming parameter n. So let's store that. So we'll do store word, and the argument that we're storing is n, which is stored in register 10, and we're going to store it on the topmost stack slot. So that is that. So that is stack pointer. The number 2 is the stack pointer, and then an offset of 0 from the stack pointer. So now we've used up that slot to store the incoming value of n. So now we're free to trash register 10 should we need to do so. So one thing we can do now is take the value of n that is in register 10 and subtract 2 from that number. So we'll do this. We'll take the number in register 10 and add -2 to that, which is the same thing as subtracting or subtracting 2. And let's store that in the intermediate register 11. We're allowed to use this register because it's not an input variable to this function. We only have one variable, so x11 and 12 and onwards are available for trashing. So we'll just subtract 2 from x10 and store that in x11. In register 11 now, we want to compare that to 0. And if this number is less than or equal to 0, or actually if it's greater than, then we want to skip the return statement here and go down to here. So what we want to do is say branch, and now we need a new branch instruction that we haven't implemented yet. So let's go and find the branch instructions that are available. And they are going to be here. So we have a branch greater than or equal. So this is exactly what we want. Now it's going to have the same major opcode as the other instructions that are doing branches, except the funct3 field will be 101. Nice. So we can probably safely add this without implementing it in a unit test. So let's add BGE. So the first thing we do is we add it to our mnemonics. Let's put it next to the other branch instructions, BGE. And while we're here, I noticed that goto is not used anywhere. And since that isn't an actual RISC-V instruction, I'm going to get rid of that. Same thing goes for BNZ. That goes away. Okay, so now we have BGE added. Now we need to add it to our assembler. And BGE is going to be handled very similarly to BNE. So all I have to do is find BNE and then copy that value and paste it over here. Here's BGE, and then the bit pattern was 101. So that assembles BGE, and then finally we go to the emulator, and now we implement the emulation of the BGE. So let's find BNE. It looks like we haven't implemented the branches. Let's take a look at the major opcode. The major opcode is 11000011. So 11000011. Here we go. Oh, we haven't written comments for this. That's why we couldn't find BNE. So let's do that. And then for the case of 101, which is a BGE, then we say if registers source 1 is greater than or equal registers source 2, then IPTR next is IPTR plus uint of m. There we go, and then finally break. That should emulate BGE. Let's go back now to our program, and we will use BGE. So if after adding -2, the contents of register 11 is greater than or equal to the contents of register 0, which as you recall is always 0, then we want to go to the complex case, this case where we multiply with the factorial of n minus 1. Let's just go to a place called complex for now. We haven't defined what that is yet, but first we're going to handle the base case in our recursion, which is very easy. All we have to do is make sure that we return a 1. So what we can do is we can say asm add I, and remember now that the return value of a function in our calling convention is also using register 10. So into register 10 we add to the register 0 the value 1 immediate. So this takes the immediate value 1, adds it to the contents of register 0, which is 0, giving us a 1, and that gets stored in register 10, and now we're done. But before we return, we have to clean up the stack. So we have to undo this operation that we did here, and the way to do that is just to add 4 back to the stack pointer or register. Let's add a few helpful comments here. We'll say this is base case return 1, and here we'll say restore stack pointer, and then finally we want to return, so we'll use jaller. We discard the return or the next. We don't need to keep track of the next, but we do want to use whatever is stored in register 1, which is the return address, and we add no offset to the return address. So there's that code. But if we are greater than or equal to 2, then we want to go to the complex case. And the complex case is supposed to take the value of n minus 1 and compute the factorial of that, and then take the return value and multiply it by the saved value of n. So remember, when n comes into this function, starting here, it's in register x10. But after the call to the factorial, x10 will contain the computed value of the factorial of n minus 1. And we need to multiply that by a saved value of x10, or register 10. So what we'll do is we'll take the current contents of x10 and just call ourselves, jump and link, and we need to remember a return address in register 1. Oh, but that would overwrite the register 1 that we are hanging on to. So we need to actually reserve 2 slots on the stack. One for the return value and one for the value of x10 that we have to hang on to during the computation. So we'll store the return address, which is in register 1, at stack slot 4. So these 2 store instructions store the return address of our caller and then the input parameter 10, x10, because we need that after we've made our recursive call. So we call ourselves, and this should be easy enough to compute. We're going to call backwards, so this is minus 4 bytes, minus 8 bytes, minus 12, 16, 20, 24, 28, 32. So we want to go backwards 32. But I made a mistake here. We have to subtract 1 from x10. So let's do that first, and that means that the 32 becomes 36. So this takes the value in register 10, subtracts 1 from it, and stores the value back in register 10. Then we call ourselves with this smaller decremented value now in register 10. And then after we return from that call, we now extract the value that we stored previously in the stack pointer, this value right here. So, but we have to be careful of which register we restore that value into, because we want to keep the value that came out from the recursive call here. That's already in x10. That's the factorial of n minus 1. So we can write x10 equals factorial of n minus 1. So what we want to do now is take the old value of n and move it into another register. Why not x11, which we've been using as a trash register all along. So we'll say load word into register 11 from the stack pointer offset 0. So now we have grabbed the old value, and now we can safely multiply these two together, and remembering that the result we want to deposit into the return register, which is x10. So this would be a multiplication where we put the result in register 10. We take the 10 that we got back from the function call, and also the 11 that we got from restoring the saved value of n. And let's put a comment here, save the n register and we'll write another comment. Like so. So we're almost done. What we have to do now is adjust the stack, and we have to do that in both cases, both in the base case where we have to adjust it by 8, which is something I neglected to do. So now that stack is balanced, but we need to do the same thing here. And in this case, we not only have to restore the stack pointer, but we also have to restore the return register. And we do that before we restore the stack pointer. We'll say load word into register 1 from the stack pointer offset 4. Note that we don't have to restore the return address in the base case of the recursion, because in this base case we're not modifying the register x1. So in that case there's no need to restore it. But in the recursive case we are destroying it. This jump and link instruction will destroy the value of register 1, and so we need to restore it before we return. So that's what we do here. We'll restore. So now we restore the return register that we got when we entered the function, and then we return. Now we need to compute how far this jump is. So again, in groups of 4, we're jumping forward to this complex case. So that's going to be 4, 8, 12, 16 bytes ahead. 4, 8, 12, 16, yes. And we'll write skip the base case if n is larger than or equal to 2. Okay, so this in theory should compute the factorial. So all we need to do now is prime it with a call. So we'll go down to the place where we evaluate the emulator. We'll take it here, and the emulator will be given a register value in x10. And we'll also need to set up the stack pointer just like before. So let's grab this existing code from our previous run. And what we'll do is we'll say that register 10 will have the value 10. We don't use x11 as an input parameter. And then the result will be stored in register 10 coming out. So if all is well, then this should result in the correct answer. Let's give it a try. And a whole lot of nothing happening. So let's stop and turn on the tracing again to see what is going on, because it looks like we are not returning from our function ever. Oh, yes, this is a problem again. We don't have a way to terminate the program. So we need to write a little stub piece which actually invokes the factorial function and then stops. So what we'll do is right before all of this, we'll say asm jump and link, and then jump forward to somewhere, and then we'll use the int to just stop, just right like we did last time. And the factorial will be jumping over to address 4, address 8. So this should fix the problem. And we'll need a third argument here for invalid. Okay, so maybe this will work a little bit better. So let's try running this. No joy. Okay, so let's stop and turn on the tracing to see what's going on. Let's go to the emulator. And the emulator had this statement at the top. Let's see what's going on. Interesting. We don't even get that far. Something really odd is going on here. Let's go back to the main program and see what is going on. So we'll put a breakpoint. Clearly we should reach this point. So let's try hitting that breakpoint. There we go. Here's our factorial function evaluation. We can get rid of this breakpoint for sure. We know that this works. Okay, so here's our assembler, and we're going to assemble our program. It could be that our BGE implementation is wrong. We'll find out. Huh, we did complete an execution, but our output result is wrong. So let's debug this. So we'll go and put a breakpoint in the emulator. And put a breakpoint right here. And then let's run the program again. So we know this works. We can proceed. All right, so here's our first instruction. This is just going to call into our factorial function. So let's just perform the call. And that gives us a store of the return register, and then we get the store of x10, which should be 10 at this point. Good. So after doing that, we now run the next instruction, which should be an addition. So we're adding the value of, oh, maybe this is the problem. This should be an add immediate. Yes, in fact, this is our problem. And a better assembler would have caught this. -2 is not a valid register number, but here our assembler blindly accepts it. This should be an add immediate. And that explains why we are failing. So let's stop the debugger and run it again. Let's let it run. And now we can see that the C# result and the assembler result match again. So we've successfully implemented a recursive function, the factorial function, in our assembly language, with a little bit of painful debugging. But this is the nature of assembly language programming. You really have to be careful because there will be no help given to you by the assembler at all. And our assembler is a little bit dumber than most assemblers, but even the most clever of assemblers will have problems discovering our bugs. There's a reason why we don't program large programs in assembly language anymore, because it's just too error prone. But at the same time, if you really want to get down to the metal, this is the best way to write the most performant code possible. You have absolute control of the instruction stream as the programmer, but it also gives you the responsibility of making sure that your program is completely correct. So, having said all that, we can now take a step back and see what we've accomplished. We have written, first of all, a assembler which knows how to take this machine or assembler language looking stream of instructions and convert them into RISC-V machine instructions. And then we've also written an emulator which understands those encoded machine instructions and then performs the operations that those encodings indicate. So we have, so to speak, two sides of the same coin. We have the encoder, the assembler, and the decoder, the emulator. But so far, all we've done is memory manipulations and some arithmetic. We haven't actually done any I/O at all. And that is going to be the topic of the next session. And I/O can mean any sort of interaction with the environment outside of the emulator or the CPU emulation itself. We would, for instance, like to be able to write stuff to the screen or write stuff to a file. We might want to allocate some memory or open a file. All of those operations are typically accomplished using a mechanism known as a system call. And we will look at how system calls are implemented in RISC-V, and we will implement one system call that will allow us to finally reach a point where we can write the hello world message. Until then, dear viewers, I wish you a pleasant time, and thanks for watching.